Alright, this is a test presentation of widening and narrowing in Typescript. It's based on the wiki page. That if you like reading things instead of watching videos, you can go there and read that instead. So, it's a whole bunch of related concepts in Typescript, which a lot of them have the name widening, narrowing. Some of them are internal, some of them are external. So I wanted to talk about them sort of all at once, and that way you can sort of get a whole feeling for how they're working with each other. So widening is the first concept. It's actually kind of minor, but it was there first, so I got the short, good name of widening. And really all it does is treat null or undefined as any. And it only applies when strict is off. This is from the old compiler, where there's a null and undefined type inside the compiler, but outside the compiler to users, there was no such type, and so it had to be converted to any. So in the current compiler, when you have the type, when you have the value null, it has the type null. So value null has type null. When you assign it to x, it widens to any. Again, this is when strict is off. Obviously, when strict is on, then x just has the type null. And this happens on variable declaration. So when you're assigning something or when you're initializing a variable with something, null gets widened to any, and then x has type any, which means anything can be assigned to it. All right, so that one's pretty simple. And again, it has a nice short name. It should be called just like null widening or something, but it's called widening because it was there first. All right, the next concept is also internal. It lets you treat a non-object type as an object. So that's kind of an odd concept, and this is an ad hoc thing. It's part of the compiler because we need it, and it doesn't really particularly make any sort of set theory sense necessarily. But what it does is sometimes you'll ask for the properties of something, and if you're working with a primitive type like lowercase number, that doesn't actually have any properties inside the type system. It's just a primitive. And the apparent type is the object type that goes with the primitive type. Obviously, if you have an object type already, then apparent type is just that type. But you sort of ephemerally or temporarily need to say, well, I have lowercase number. If I were to have some matching type, what would it be? Well, it would be uppercase number. It's like sort of the boxed type for number. And that's the one with the properties on it. So I'll show you that in a minute. Actually, let's go to the playground right now. Okay, so here we have the same thing. We've got number. And number doesn't actually have any properties. ToFixed does. Notice actually the tooltip even tells us. So there's uppercase number dot ToFixed. And if we peek at the definition here, you can see that there's just a built-in interface. And it's interface capital number, there's an interface capital Boolean, that has all of the methods for numbers and Booleans. And in fact, if you wanted to, you can, in a global context, in your own code, say interface number and glom things onto number, which sort of reflects the monkey patch ability of JavaScript. You shouldn't do this, but you can, and so it's in the language. And if there is no interface number at all, then lowercase number will not have any properties. Like, say you set up your tsconfig wrong or something. This also actually applies for type parameters. So type parameters also don't have any methods. And sometimes you also want to be able to access properties, which you can if there's a constraint. So here's a constraint extends node. And node's over here. There's this type. When you say node.parent, T doesn't have any properties. However, node does. And so because T is guaranteed to extend node, it's guaranteed to have at least these properties. Might have more. It has at least these. And you can see this, that this is actually coming from node, because this doesn't say T extends node. It actually just says node. So node is of type T extends node, but parent actually comes straight from the interface node. It's not extended in any way. It's just the base one. So you can see that the apparent type is kind of like sort of base properties in an object-oriented language where you refer to a base property and it's not in the class you're currently using, it's somewhere else. But this is a much more temporary relation where the compiler just needs to know, hey, I'm asking for properties on this thing that can't possibly have properties. Where should I look instead? All right, so this is a table of all of the mappings from a parent type. The important ones are over here, where lowercase string goes to uppercase string, number, big int, boolean, simple, object. All of those map to their box types, and then those are the things with actual properties like to fixed or to uppercase and so on. There's a bunch of other sort of weird obscure ones. The one we talked about is t extends a goes to a. So that's some type parameter that extends some type, just goes to that type. And then there's some other ones that are like I said, they're pretty obscure. All right, so next up is literal widening. It actually happens a lot more than null widening does. And I say it's internal mostly because although it usually works without you having to think about it, sometimes it is easier to use the language if you know about this concept and how to use it. So literal widening treats a literal type as its base type. And you can chain that with like a parent type, obviously. So if you have a literal type, quote, foo, it's can be treated as string. 101 can be treated as number. False as boolean, and then some enum.member can be treated as some enum, because in Typescript, most enum members get their own literal type. So they're sort of like the equivalent of a number or a string literal type. And then they have a parent type, some enum or a base type, some enum that's sort of like the equivalent of string or number. Literal widening crucially only happens to types that originate from values, not types, which is a little confusing. So if you actually have x:1, so declare const x, it has the literal type 1 in the type annotation. Literal widening never happens. X is just always going to be 1. And anything that interacts with x will also always be 1. However, if you have const x equals 1, well, your type there is actually coming from your initializer, and it's inferred from the value. So you have the value 1, which has the type 1, and then const x also has the type 1, and that type could widen. However, it doesn't in this case, because literal widening only happens at the point where a type hits a mutable location. And let's look at the playground for that too. Yeah, here we go. Okay, so simple, the thing I just showed you. 1 has a type const 1 equals 1. This is hard to talk about. I'm going to change that to constant. So the literal 1, the value, has type 1, and you can't see that here, but trust me. And then constant also has type 1 because it gets its type from its initializer, and it's const, so there's no reason for it to widen. But if you contrast that with let num equal 1, well, 1 is still 1, it's a literal, but when you assign it, it literal widens in the same position that null widening happens with strict off. It literal widens to number, so let num is number, and that's so you can do like num++ or num equals 3 or whatever, and that's what you want for let because it's mutable. The sort of surprising part of this rule actually is that if you have constant is still type 1, but its type right here, the literal type 1, when it's assigned to wat, also widens. So wat is now number. It's not literal type 1. And that's non-obvious. Why would you do that? Well, it lets you write for loops with const bounds. So you've got like const start equals 1001, const max equals 100,000, and maybe these consts are off somewhere else in your program, and thousands of lines later you're like, okay, for let's I equals start, I is less than max, I plus plus. I want to be able to mutate I. But if it has a constant type, 1001, I'm not able to do that. So I want to be able to assign from consts to mutable things and then mutate the mutable things. And so that's why that rule is that when you have a constant the literal type for the constant that widens when you assign it to something that's mutable. All right, so that's literal widening. Okay, so that's all I have time for now. I will talk about narrowing again in another time.